All right, welcome to another exciting episode. Thank God it's Friday, February the 28th, the last day of February. We are cruising into the end of this year. Okay, the AP test is catching up to us. We just have a couple of units left to do, and then a couple of mock exams, and then it's summertime. All right.
So basically, it's
Yeah, we're almost there. That's why I said I'm trying to be optimistic. So let's go over these multiple choice questions. And we want to look at the big picture, the concepts behind the question, not just the question itself. And that's how you need to study, is study the concept and not just the question. So I don't know how you want to kind of go through this. You've already submitted, you already have all the answers if you submitted it. But I want to kind of talk about the concepts behind it. So the first thing is when we're looking at this is not a very common unit for pressure, but kPa, kilopascals, is the actual metric unit for pressure. 101.3 kPa is 1 atmosphere. So basically it's saying it's at 1 atmosphere of pressure. Now, in America, we use PSI a lot. So if you ever have to put air in a car tire, you're going to go and it's going to tell you, and if you ever need to know, you open up the driver's door and there's a little patch on the inside of the driver's door on the frame that says what tire pressure you're supposed to have on your car tire. And it's always cold tire pressure, meaning before you've driven on it. When you drive on a tire, because of friction, the pressure goes up about 3 pounds per square inch, PSI, just so you know. Okay, that's totally on my information, but it's also going to give it not just in PSI, but it's going to give it in kPAs. If you ever have to put pressure in, all of the pressure gauges, anything you use is going to have both PSI and kPAs. We use PSI in America, the rest of the world uses kPAs. kPa is the actual SI metric unit, just like Kelvin is for temperature, kPa is the metric unit for pressure. So 101 kPAs is 1 atmosphere. So now what's the significance on this graph right here? What tells us anything on this graph, on the data? What is significant?
it reaches equilibrium.
How do I know when it reaches equilibrium?
Because the pressure stays constant.
Okay, it's when the pressure stays constant. It's the equivalent of the graph going horizontal. That's going to be my indication. So I know that at 1.5 minutes that I've reached equilibrium. Now, does that mean that all the reaction has stopped? What does that mean at equilibrium?
The forward rate equals the reverse rate.
Forward rate equals the reverse rate. Okay? Forward rate equals the reverse rate. So a sample of acetone is placed in the container. Container is sealed and attached to a pressure sensor. The container is allowed to sit on the table for a few minutes as the pressure is monitored at regular intervals. At the end of 2 minutes, now look, notice what it says, and I don't know if you can underline or whatever. Some acetone liquid remains in the container. What's the significance of that?
Not all of it has been used in the reaction. It's gone to completion.
Now, it hadn't gone to completion. If it went to completion, it would all evaporate. Okay? In order to be at equilibrium, you have to have some of both, reactant and product. Okay? So if it didn't have some liquid still in the bottom, then you wouldn't know if you had really reached the maximum amount of vapor that could be in the container or not. But because there's still some liquid and then the pressure remained constant, that means now some is still evaporating, but now the rate of condensing is equaling the rate of evaporation. Okay, so it's kind of going both ways. So it's important here to know, and when we talk about KSP, a saturated solution, you always have to have some solid remaining, because you don't know it's saturated if there's no solid sitting on the bottom. There still might be more room for it to dissolve. You always have to have both reactant and product for it to be at equilibrium. So the fact that we have some liquid remaining in the container is important, because it tells us that, okay, it can be at equilibrium. Now, that's going to be important when you go and you look at your answers, okay, because it's going to say, okay, first off, the acetone heats up over time. Well, what would have caused it to heat up? Does evaporating heat up things or cool them down? When sweat evaporates off you, do you heat up or cool down? You cool down. Evaporation is actually a cooling process, not a heating process. And so I don't even know where they're getting, this is just kind of a made up answer. Because there's no mention of heat, I think the temperature remained constant, or whatever. The acetone, but here, the acetone is completely vaporized. Well, what tells us that that didn't happen?
There's still some liquid.
There's still some liquid, so the prompt itself answers tells us that it can't be that one. Okay, because it says that there's some liquid, so it's important kind of to read. Okay, that, here's another test taking. The longest answer is generally the right answer. Okay, so when if you're really unsure of the answer, pick the one that's longest in the explanation. The acetone vaporizes from the liquid at a constant rate. The rate of condensation increases until it becomes equal to the rate of evaporation. So what is that saying? Until the two rates equal one another. So in simpler terms, until it reaches equilibrium, and then the pressure stays constant. Okay, that's just the definition of equilibrium. And then the acetone vaporizes from the liquid at a rate that is fast in the beginning and then slows down until the vaporization process stops completely. What's wrong with this one?
It doesn't stop completely.
It doesn't stop. Remember, equilibriums, it's dynamic equilibrium. Equilibrium means the forward rate and the reverse rate are equaling. Doesn't mean it stops evaporating. It simply means that for every one that evaporates, one's going to condense. It's a dynamic, constantly changing equilibrium. Okay? The pressure stays the same, but some evaporates, some condenses. The forward rate equals the reverse rate. If you're going to have forward rate equaling reverse rate, then the process can't stop. Okay? So those are big concepts as far as just what equilibrium is. So think about those things. So a lot of times you can learn a lot from the wrong answers as well as the right answers. Okay? Now I kind of don't always like having the answer shown, but I haven't been able to figure out how to show this without it, but you already have the answers anyway. So we have this NO2 going to N2O4. Now, totally oh my information, but NO2, again, if I look at the Lewis dot structure of NO2, I have 5 plus 12, I have 17 electrons. So when I do the Lewis dot structure for this, when I do the Lewis dot structure for this, okay, I do oxygen, oxygen, 2, 4, 6, 8, 10, 12, 14, 16. What do I do with that one electron? It's just going to go in the nitrogen. It's a free radical. It's highly reactive. So this can dimerize. This can react with another NO2 and form that bond right here with the nitrogen. And by the way, we're going to form a double bond too. Okay, so it can form a double bond, single bond. Okay, but then you get the bond between the two. So it dimerizes. That's why anything that has that free radical, they can kind of come together. So that's kind of the equilibrium. Is it staying apart, or is it, coming together using that unpaired electron? Yeah, you don't need to know any of that for this reaction. I just, think that's cool. So I just can't help myself, but sure. So it says NO2 is a sealed tube and placed in a bath at 30 degrees. So if it's in a water bath at 30, what does that mean about the temperature? Is it going to be changing? If you're at 30 in a water bath, what do we know about the temperature? Is it going to vary from 30? No, it's going to stay. That's the whole idea. We're at constant temperature. Keeping it in a water bath is staying at 30 degrees. Observations and changes in color, pressure, and mass. Which of the following is an observation that would best support the claim that the reaction represented above has reached equilibrium at 30 degrees? Okay? Now, let's just talk about each one. The total mass of the system remains constant because the amounts of reactant and product do not change with time at equilibrium. Is that true? Does the mass change? No, it's the law of conservation of mass. That's 100% true statement. But does it tell us anything about whether it's at equilibrium or not? No, because if it's all reactant and no product, it's going to be a mass. If it's all product and no reactant, it's going to be the same mass. If it's in the process of reaching equilibrium, it's going to be the same mass. The mass is never going to change because it's a sealed container. So it's 100% true, which is what makes this a kind of a hard question. is 100% true, but it has nothing to do with telling us, is it at equilibrium? Okay? Now, the color of the system changes from brown to completely colorless. Well, if it goes from brown to completely colorless, is that at equilibrium?
No.
No. That means it's going to completion, not at equilibrium. The total pressure of the system decreases. Now, this is the right answer, but so why would the total pressure decrease?
Less moles.
Less moles of
Gas.
Yes.
gas. So let's just say that I had 2 atmospheres of pressure right here to start with. Okay, so that was it, 2 atmospheres of pressure. And then it goes towards if the reaction went to 100% completion, okay, it went all the way to completion, 100%, what would my pressure be at the N2O4?
1 ATM.
1 atmosphere, right? Because 2 molecules are making 1 molecule, so you have an half as number of molecules, you're going to have 1 atmosphere. So, where is my equilibrium pressure going to be?
In between 1 and 2.
In between 1 and 2 somewhere. Depending upon, we don't know what the value of K is. We don't know if it's product favored or reactant favored. If it's reactant favored, it's going to be closer to 2. If it's product favored, it's going to be closer to 1, depending upon what the value of K is. It doesn't say. But I know that the pressure is going to be somewhere in between. So the pressure is going to decrease, then reaches a constant value because the amount of reactant and product no longer change. So once I get to equilibrium, now I'm going to have a set amount, so it's going to be somewhere in between that 2 and the 1. And then the temperature of the system remains constant because the temperature must be constant at equilibrium. Okay? Now, the temperature, again, that's kind of true. The equilibrium constant is temperature dependent, but does the fact that it's staying at 30 degrees tell me if it's at equilibrium or not? No. All right. Okay, so what's the just importance here? How do I know when equilibrium is reached? When it goes flat. So it's at what point? D. Okay, there's no more explanation. Okay? Now, I'm not crazy about this question. I think I told you, I don't know, about 4, 5, and 6. I don't like the way that they asked this. But let me try to make this into something not equilibrium. Is this a good representation of silver chloride solid dissolving in water? Is it accurate from that point of view? Shaking your head yes, why?
The H2 molecules are like orientated correctly.
Okay, so this is my Cl minus, right?
Yeah.
This is my Ag plus. So you say they're oriented right.
Yes.
The oxygen part is pointing towards the silver. The hydrogen parts are pointing towards the Cl minuses. Okay, but so if they ever asked you to draw something like this dissolving, this again is how you draw it. Now I would actually try to make them actually touch. But notice you don't have to label the hydrogens or the oxygens, you don't put charges on it, you just orient them the right way. Okay, so well, how else can we tell that it's a good representation?
The Ag plus and Cl minus are proportional.
That's right, they're proportional 1 to 1. Okay? But does it tell us if it's at equilibrium or not? Now, there's no real way to look at a picture like this and tell, unless maybe they had something like that was coming down and that was going out to that, you know, showing something where it's some's dissolving and some's precipitating back out. But it's very hard with a picture to show equilibrium. So, I mean, whoop. My hands all blue. All right, so that's just basically that. So it's not a good representation because it does not illustrate the dynamic equilibrium. Again, what does that word mean? The changing, some dissolving, some precipitating. Okay, so we have to look at the words. This is the exact same thing. Okay, almost the exact same response, almost the exact same answer. It only shows the system at one point. You don't know if it's completely reacted or not. So I'm not going to dwell on that. And I think this one's an even stupider question. But you're going here. Okay, so you're making 0 here. You have 1 here. You have 1, 2, 3 here. And you have 1, 2, 3, 4, 5 here. So you're still making the XY, right? Does it show any XYs? Does it show any constant concentration of X and Y? So are we at equilibrium yet? No. Okay? The forward reaction is always faster from 0 seconds, so more products are always being formed. I mean, I just don't think those are good particle representations. All right, so now we get into good problems. Once we got past those diagrams. Now, this is why I vehemently, and hopefully somebody at College Board is watching this video, okay, I vehemently disagree with this all being on a computer. Because what we need to do is make our ice table right here, and you need to be able to draw it. I pray that they at least let you have a piece of scratch paper, okay? Because I want to put my initial and I want to put my change. So my initial here is 0.3. But at equilibrium, it tells me that it's 0.24. So what's my change? Minus 0.06. So since this is 0 and 0, now it even tells me that at equilibrium that I have 0.03 of this. Okay, so this is going to be plus what? 0.030. So this is going to be plus 0.030. So I want to be able to write that. I want to be able to make my own ice table. And you can't do that on a computer screen. Okay? But you need to do that somehow. So now you have to calculate KEQ. So KEQ is going to equal simply this times that. So 0.030 squared over 0.24 squared. The only one that comes out to this, so the because doesn't matter. Now, without even doing the math though, the because, we know this 1 to 1, these two have to equal each other, right? This is the only one that shows those two equaling each other. So without even doing any math, this part is true. So you could do it in one of two ways. If just look at this and know that, okay, well, those have to be the same. It's got X and X. Okay? Or you plug it in and get the value, and the only one that comes out to the right value is this one. So this is right for two reasons only. This is the only right answer for KEQ. This is the only right answer for the concentrations. Okay? Ice, baby. Make your ice tables. Anytime they give you this kind of information, set up, figure out what your X's, your changes are, your initial change in equilibrium. And to me, just seeing it graphically like that is so much better. This is another one that's exactly the same. So again, I'm going to start with 1 atmosphere and 1 atmosphere, 0. And then it tells me again that at equilibrium, this is initial, my change at equilibrium. I'm going to have, they give you more than you even need. If they just gave you that, what do I know my change is? Okay, this is plus 0.8, so this is going to be minus 0.8, minus 0.8. So this is going to be 0.2 and 0.2. Okay, so then again, you know it's going to be 0.2, so I know these are 0.2, so I can eliminate that one and that one just by that. Okay, then you have to just actually plug in. So again, I'm going to get 0.8 divided by 0.2 squared. Well, 2 times 2 is what? 4. 480 divided by 4 is 20. Okay, so even though I'm not keeping track of my decimals, I know that it's got to come out to a 20. 0.2, 2.0, 20, it's got to come out something because it's got to be 8 divided by 4 or something. Right? So without even putting the calculator. Now, last year was the first year that you were allowed to use a calculator in multiple choice. So you wouldn't have to do the mental math, because I know that some of y'all can't, 2 times 2 is kind of pushing it. Uh, I know I'm being mean, but you guys don't like to do anything mental math wise. You're very calculator dependent. But you could do it. They used to make you have to do something like this in your head. Okay? This is probably off of an old test that actually made you to do that mentally. Okay? And you guys all get intimidated by the mental math. Alright. Moving on. I didn't like this question either. I'm only going to spend a second on it. Okay? Let's look at the answer. Kc is constant at a constant temperature. So here, two identical vessels, each contain equilibrium mixture of two gases at the same temperature. At that temperature, which is a certain temperature. But it doesn't matter what the temperature is. Kc is given as 1.2. The concentration in the second vessel is twice the concentration of the first. Well, if we're going to keep the same ratio, what must be the concentration of the other one in the second? Well, it's got to be twice the concentration as the first, because it's got to be in the same ratio. This still has to equal 1.2. Okay, so if you double one, you got to double the other one. Just whatever they are, you got to just keep them in the same ratio. Because it always has to equal 1.2, because the temperature doesn't change. What's the only thing that's going to change the value of K? Temperature. All right, now we get good questions. The equilibrium reaction, 0.1 molar. I have 0.1 molar of this. Okay? Based on the magnitude, what does it mean, the magnitude of the equilibrium constant? The size of it. So I look at this right here, that's the magnitude. Big or small? Small. And this is products over reactants. So what does that tell me? What do I have more of? Reactants. A little bit or a lot? A lot more reactants. So I'm going to have, I start off with 0 and 0, but when I talk about my minus x, my plus x, and my plus x, this is going to be a very small number, right? I get that from the magnitude of the K. So, let's look at the wrong answers here. The equilibrium concentration of BRO minus will be much smaller than the equilibrium concentration of H3O plus. What's wrong with that statement?
They're both on the same side.
And, well, true, but
The same moles. So
it's going to be X and X, right? Are they going to be different? They're going to be exactly the same. The equilibrium concentration of BRO minus will be much smaller than the equilibrium concentration of this, because what do the two less than signs mean?
Much less than.
Much, much less. Significantly less. Way less. Okay? Now, let's look at C and D. The equilibrium concentration of H3O plus will be much smaller than BRO minus. That's the same, just kind of reverse of this question, right? But what do we know about these two things?
They're the same.
They're the same. So we know that's not true, that's not true. The equilibrium concentration of H3O plus will be much larger than HBr. When would that be true?
If the products are greater than the
If this was a plus 9 instead of a minus 9, and then we would say that KEQ is much, much greater than 1. Then that statement would be true. You follow me on that? So notice they're wanting you to understand the significance of how big or small K is on the effects that it's going to have on the equilibrium. All right. You're not that tired of it. You're good. This is darned exciting. It's got to give you an adrenaline rush. Keep you going. All right. I should start a sleep company. Here we go. A certain SO2 and O2 react with SO3 quantum equation above, and evacuated containers can each with 1 atmosphere. So 1 atmosphere and 1 atmosphere. See again, I like to be able to write this. So if I'm taking this test and I have to do it on a computer, I'm going to have a scratch paper and I'm going to write the equation out and I'm going to put my ice tables just kind of my givens. I need to be able to see my givens. I know that theoretically you can underline things with a blue book, you know, you can highlight, but to me, just being able to see it like this over the equation. And again, AP, if you're listening, it's stupid to do it all in a computer. We teach you how to write on paper. It's proven it's going to be better. Proven it's better. Anyway, sorry. It's just not in your best interest, and I'm sorry I got your best interest in mind.
Oh, I don't.
So, which of the following is closest to the partial pressure? Now again, we're going to look at this KP. This one's big. What does that mean?
Products are bigger.
Just a little bit bigger?
A lot.
We can assume, because of this, you assume, notice it says approximately, assume 100% to the right. Okay? Which means, which is my limiting reactant here, and how do I know?
The two is because there's more moles of it.
It's, for every one of these, I need 2 of these. So if I have 1 atmosphere of this, I would need 2 atmospheres of this. So if I have 1 atmosphere of this, how many atmospheres of O2 do I need?
0.5.
So if this is minus, if it goes to completion, this is minus 1 atmosphere. So I'm going to, at equilibrium, I'm going to have 0 basically, because we're assuming it's going to completion. I mean, you're going to have a fraction left, but not much. Close, approximately 0. Okay, so how much of this is going to react?
0.5.
Minus 0.5. Right? So we can say 0.5 atmospheres because KP is very large. Nearly all is consumed, but an excess amount of O2 remains. 0 because KP is very large. Nearly all the SO2 and O2 are consumed. Well, why aren't they all consumed? Because it's a 2-to-1 ratio. 1 atmosphere because KP is very large. The system is already near equilibrium. There'll be very little change to the partial. Well, how can they be at equilibrium when you just put it in? You know, if you don't have any of this, okay, and then 1.5 atmospheres because KP is very large, the decomposition of any SO3 that forms increases. Well, if it's going this way, is this going to be coming back this way and decomposing? No. This would be if it was very small. It would be coming back the other way. All right. 12.1. Now again, 10 to the 37th. What do we assume? It's going all, completely towards the products. Okay? Now again, I have 0.1 mole of this. Okay? It tells me that. And then the 500 milliliters, if I have 500 milliliters of 1 molar copper, how many moles of copper do I have? We need to be able to do this. How many liters is 500 milliliters?
0.5.
0.5. And then times 1 mole per liter. So how many moles do I have? 0.5. So I have 0.5 moles of this and 0.1 moles of that. So it's 1-to-1. So obviously this is my limiting reactant, right? So we should be able to just do that in our head real fast. Now, almost all the zinc will still be in the beaker with no visible. Well, if I have 10 to the 37th, will almost all of this still be here? No, just the opposite. It's almost all going to be gone. About half the zinc. Well, again, 10 to the 37th. So they're saying 0, half, 2/3, or all of it's gone. All of it's going to be gone. How do I know that? 10 to the 37th. Now, I also have to know that I got plenty of copper to react with it. So I'm still going to have some copper left over, but all the zinc is going to react. Okay? So again, look at the concept. Big K, 0, half, 2/3, all went. Okay? So that's 2 or 3 questions in a row asking about the significance of K towards the position of the equilibrium. Okay, that's what we have to, that's the concept that you study. Now, these next 3, I see them all the time on the multiple choice questions that get released, okay? So these next three are very common on AP tests, multiple choice. Thus, they're very common. Where else? Okay, hint, hint. All right, make sure of this type. So what's the difference here? The table above provides KEQ. Which is the following correct? So how do I get to reaction 3? What do I have to do?
Like add
Hess's
reaction.
law stuff.
Yeah.
Gotcha.
Hess's law stuff.
Okay, but what specifically?
You have to.
Flip reaction
What did you say?
to flip the second reaction.
Flip reaction 2. Okay? So what does that mean about K?
Is it
1 over K2, right? So now once I flip that, I'm going to add the 2 together, right? What do you do to K's when I add them together? Multiply them, so it's going to be K times K1 times 1 over K2. So if you reverse an equation, you get the reciprocal value of K. These are very important, okay? Multiple choice questions all the time on these, okay? Josh and I'll be very discreet. You add equations together, you multiply the K's. So now here's the same type of question. How are these two equations related?
They're the same, but they're like opposite.
This one's just the reverse of that one, right? So how does K2 relate to K1?
1 over K.
1 over K1, right? So what's the only thing we need in order to get K2? Value K1. All these other things aren't going to help us get the constant. All right, last one. What again? In order to get this equation, what do we have to do to these equations?
You have to multiply the second one
By
by 2.
By 2 and
Flip it.
flip it. So what does that do to my K?
You square it.
1 over K2 squared, right? So then you're going to add the equations together. So what are we going to do to the K's?
multiply.
So it's going to be K over K1 over K2 squared. Okay? So these are just, this one right here makes you have to know everything about what happens to K. You reverse it, it's 1 over, you multiply it, it's raised to the power, you add them, you multiply. Great question, just saying.
Can it be the exact same question?
Okay? Now, this is a classic AP multiple choice question. Okay? Classic AP because they give you all kinds of stuff to distract you. You had, because when I was going over it in fourth period, I started falling into writing everything down. And then when I actually got to the question, it was so much easier. The formation of iron to the ferrothiocyanate ion in an aqueous solution is represented by the chemical equilibrium shown above. A light red-brown solution is prepared, combining that many mils and all that stuff, and 37 milliliters of water that has been slightly acidified. Wow, that's phew, this must be a hard question. If an additional 1 milliliter of FeNO3 is added, which of the following predicts what's going to happen? So I have it all set up, I've added all these things in, and now I add in some more FeNO3. So FeNO3 is going to be which one of these? It's going to be that one, right? The nitrates are just a spectator. You can't just get Fe, you got to have it with something, but it's the Fe. So what's going to happen to my reaction? It's going to shift right and become more brown. So all of this stuff really just means I put it all in and I got an equilibrium. It's all distractor.
I wish they would just ask the question.
Okay? So it's really just, okay, so I put some more of this one in, what happens? Okay, now here's this reaction. So you start off, they give you all the information, 1.1 mole in 1 liter. The reaction mixture has quickly reached equilibrium. After 20 seconds though, the chemist reduces the volume of the equilibrium system by half while keeping the temperature constant. What's the importance of keeping the temperature constant? K doesn't change. Okay? Which of the following predictions about the yield of NaCl? So they're asking which way is the reaction going to shift? What did we say? If you make you're decreasing the volume of the container, what's the reaction going to favor?
Less moles.
The side with fewer moles of gas. That's all you need to know on this one. The side with fewer moles of gas. Which side has fewer moles of gas? The right side, the product, correct? It's 3-2. So that means the NaCl is going to increase. What happens if we expand, made the volume bigger? Goes to the side with more moles of gas. So again, this is a Le Chatelier's principle question. What's going to happen? Okay? So, by having, now, it does talk about the pressure doubles. Now look, you can even eliminate, by having the volume, the pressure is reduced by half. If you have the volume, is the pressure going to reduce? By having the volume, the pressure is reduced. The pressure increases when you make it smaller. A bicycle pump, you push the piston down, push the gas into a smaller container, the pressure goes up. So you can eliminate C and D just by that first statement. Okay? So we know that the pressure doubles, okay? So then you're gonna go, by decrease the total number of gas, thus yield the increase more product. Okay? So we just gotta look at that. So again, sometimes just the things that you know, you can eliminate some and can help you then figure out, you know, at least narrow down your guesses. All right, then I like this one. Does this one look familiar at all?
I saw that and I was like,
Yeah. We just turned that lab in, didn't we? That was the, notice what they say. A 10 milliliter cobalt chloride, okay, in a test tube, okay, cobalt chloride, that's what we used, okay, and added a few drops of concentrated HCl. That's what we did. And then pushed it from pink to blue. Deep blue solution. You guys all know what that, we experienced that. The reaction occurred in the represented equation above. Then the student placed the test tube in an ice beaker, inside a beaker that contained ice and water. Oh, so that means I'm changing the temperature. So all of a sudden now I gotta say, oh, temperature. So how is temperature? So I gotta come back. What does this tell me?
Heat's on
end of
the reactant side.
So on the, it's endothermic, meaning the heat's gonna be over here. Okay, so now that tells me, okay, so now I have my equilibrium. I'm basically putting it in ice bath, so I'm taking heat out of the system. So which way is the reaction got to go? Shift back towards this and go from blue back to pink. Okay? Now, let's revisit. What did adding water do?
Increases the concentration. Water.
No, it should do nothing. Seems like it would do nothing because it's a liquid, it's not in the equilibrium expression. But when we added water in the lab, it pushed it left and made it go back pink. Because adding water, diluting a solution does what?
Oh, it takes it to the side with more aqueous.
More aqueous ions. Okay? It's going to favor, water is going to favor the side with more aqueous ions. Now we could do this mathematically with Q. Okay? So let's just say that I added enough water where I doubled it. So the concentrations are now going to be a half. So my products are going to be half as concentrated, okay, divided by 1/2 times my 1/2 to the 4th. Okay? Now, it's whatever the concentration was, I added enough water where I decreased the concentration in half. And you could use any amount, but any amount's gonna give you the same answer. So these 1/2s cancel. So 1/2 to the 4th is 1/2, 1/4, 8/16, 16th, right? So you divide by 16, so it's gonna turn out to be 16 times more. I think I even did this when I talked about the exact same thing. Okay? So again, you could do it, now Q is way bigger than K. So as a result, it has to go towards reactants in order to get back to equilibrium. So that could be a free response type answer, a way you could answer it in a free response question. Gotta hustle. All right, so now KC is 25. Product or reactant favored? Product favored. Okay? They give you the values. KC is this. The chemical reaction shown above took place inside originated. The table provides the concentrations at some point during the reaction. Based on this information, which of the following explains whether or not the reaction has reached equilibrium? So here's the question. Is the system at equilibrium? What do you have to calculate? Q. Now, the questions help you, the responses I should say, help you to know that, oh, well, maybe I need to calculate Q. Well, what's Q going to equal? Q is going to equal whatever what? XY squared over X2 times Y2. So we just plug the values in. Well, XY is 0.2 squared over 0.1 times 0.3. Okay? So we're going to have 0.04, right? Divided by 0.03, which is going to equal 1.33. If I did my math right? So is that bigger or smaller than K? Smaller. So are we at equilibrium? Okay. So the reaction is not at equilibrium. The reaction is, so I can eliminate that one. Okay. So Q is less than K, so I can eliminate that one. Okay. So now the reaction is not at equilibrium because Q is less than K. The reverse reaction is favored to form more X and Y. No. Again, when K is less, that means I need more product. So it's going to be here because I need to make more product, get Q equal to K. All right? Now, again, I'm setting all this up like this. I'm doing a multiple choice. I'm not going through this part. I'm just going to maybe plug in my calculator and not even write it out because I can just look at the values here and know what it's going to be. Okay? Just to kind of figure that out. But you have to figure out Q. You have to know what the value of Q is. Okay? All right, well, we'll talk about the rest of these on Monday and talk about the free response questions. It'll probably behoove you to do the free response questions beforehand that were assigned, and then we're having a test on Tuesday. All right? Have a great weekend, and go Jags.